test venue. Okay, so you can just go to the room that are assigned to you, and then so that's the study guide. So it will cover chapter 4 to 7. So it includes different types of forces, circular motion, and then work and energy that we'll be talking today in this class. So let's see, worksheet. So let's see what's on worksheet 6. Yeah, I would say from 6 to 12, worksheet 6 to 12. Yeah. So.
And these will be for the word problems.
Uh-huh. So let me write it here. So for numerical problems, review worksheets 6 to 12, and then for multiple choice questions, review quiz questions. Quiz, I don't know which quiz, maybe quiz 6 from. So let's see what's on quiz 4. Yeah, so this will be on the test. So quiz 4. What's that? What's that? Yeah, you can. So if you go to your score, it will have a link. If you click that link, if you click on your scores, it should show you your response and the correct answers. So yeah, I would recommend reviewing quiz 4 to quiz 7 or whatever quiz that was the last one. So from quiz 4 to 9. Okay. So let's look at worksheet 12. So we were talking about work, and we define work as force times displacement times cosine of angle between the force and displacement. Okay, so this theta is angle between force and displacement. Displacement is denoted by delta x. Okay, so we can write this as W is equal to F times D cosine theta. So if you look at number 1, it's simply application of this formula. So you pulled a suitcase at 45 degrees angle. If you draw a free body diagram, it would look like this. So this is the force. Let's call that tension force. And this is 45 degrees to the surface. And you're applying the force of 20 newtons. So you need to find the work, how much work is done on the suitcase. So work is force. Force in this case is tension. Displacement is delta x cosine theta. Okay, so T is 20 Newton. Delta x is, you pull it for 120 meters, and then cosine theta is 45 degrees. And if you do the calculation, that gives you 1400 joules. So the unit of work is joules. Okay. It's also written as J. So that's number one. Number two. So number two involves something called work energy theorem. Work energy theorem is, if you do work on an object, what happens to that work? So let's say you push or pull an object applying some force, and it displaces by some distance, delta x. Okay. So here you're applying force, and as a consequence it is displaced by delta x. That means you are doing some work. So where does this work go? What happens to the work? It cannot just disappear. It has to go somewhere. There must be some kind of side effect. So what happens to that work? And that is answered by this work energy theorem. Okay. So let's see what that is.
How did you get 1400 on the first one?
Oh, I may be wrong. Oh, it's not 1400. Sorry, I was using 100 meters for my question, but it's 120, so it would be different. Sorry, I think you guys are right. So this is, it's 1600, right? 1697. Yeah, that's right. Okay. Yeah, in my question I had 100 meters here. I changed the distance. So, okay. Yeah, thanks for pointing that out. So it's six. Yeah, yeah. So I think that's what they are. Oh, so I just posted worksheet 12 on Blackboard. So if you are on Zoom, please download that. It should be available on Blackboard. Let's see if it is on Blackboard or not. So if you go to week 11 in assignments, so we will see this worksheet 12. Okay, so let's now talk about work energy theorem. So let's consider in this example that I just explained, work done is F delta x cosine theta, and for this particular case, let's consider that force and displacement are in the same direction. Okay, so that's F, that's delta x. That means cosine would be 0 degrees. I mean, the angle would be 0 degrees. That is 1. Okay, so this is just a special case. So W is F delta x. This may not be always true, but we are just trying to simplify the example. Okay, and we know from Newton's second law, force is given by mass times acceleration. So we can write this as W is equal to m a delta x. Okay, and then from kinematics, we know delta x is equal to final velocity squared minus initial velocity squared over 2 times a. Okay, this equation is from the kinematics that we talked in the very beginning. So we can use that here. So W is equal to m a. So this delta x is v final squared minus v initial squared over 2a. So we have a here on the numerator and a on the denominator. We can cancel those a's, and then we'll have 1/2 m v final squared minus v initial squared. So I can distribute this 1/2 m to both these terms. So we get 1/2 m v final squared minus 1/2 m v initial squared. Okay. So this quantity is called kinetic energy of an object. Okay. So this 1/2 mv squared is called kinetic energy. That's the energy possessed by any object that is in motion. In other words, any object that is in motion that has some speed or velocity has kinetic energy. Okay, and its kinetic energy is given by 1/2 mv squared. Whether it's a rolling ball or a moving car or a running person or an object thrown in air, all those things that are in motion have kinetic energy, which is given by that. Okay, so that's the kinetic energy. It is denoted by Ke. So this one is final kinetic energy of the object. Okay, so final kinetic energy is, let's denote that by Kef, and this thing is initial kinetic energy of the object. So work is final kinetic energy minus initial kinetic energy. So this expression is called work energy theorem. Work energy theorem. So this is basic principle that tells us if you do some work on an object, it changes the kinetic energy of the object. Okay. So for example, let's say there is an object, it has some kinetic energy Kei or Ke1, and if you do some work, okay, push it or pull it, do some work, then that work will change its kinetic energy. If it has 1000 joules of initial kinetic energy, then your work will either increase or decrease the kinetic energy. Okay, it will, let's say, increase to 2000 joules. It may sometimes increase or sometimes decrease. For example, if you let's say the ball is coming to this direction, and then you apply the force in this direction, then this will decrease the kinetic energy. If you apply the force in the same direction as the object is moving, then it will increase the kinetic energy. Okay. So that's work energy theorem. So let's look at number 2. How much net work is required to accelerate 1000 kilogram from 20 meters per second to 30 meters per second? Oops. Okay, so we want to find the work to change the velocity from 20 meters per second to 30 meters per second, and changing speed also means changing the kinetic energy. Okay, so when you are changing the speed, there is change in kinetic energy, because kinetic energy depends on speed. Increasing the kinetic energy means increasing the velocity means increasing kinetic energy. So we have work energy theorem. So work energy theorem is work is equal to 1/2 final kinetic energy minus initial kinetic energy. Okay. 1/2 m is common to both the terms, so you can put the common terms outside the parentheses. So 1/2 m Vf squared minus V initial squared. So 1/2 mass of the car is 1000 kilogram. Final velocity is 30 meters per second squared. Initial is 20 meters per second squared. So you do the calculation, that gives you 2.5 times 10 to 5 joules. Okay. So that's the work required to accelerate. Changing velocity means accelerating, to accelerate the car from 20 meters per second to 30 meters per second. Now, let's look at number 4 first, and then we'll come back to number 3. 4 is easier than number 3, so let's look at number 4. It's basically applying the formula for work. So let's say this is the surface, and that's the sled. Okay. So it's pulled in two ways. One is horizontally like that. That's the first case. And in second case, it's pulled at an angle. Okay, at an angle of 30 degrees. So for A, what's the work? If you pull it horizontally, it's pretty straightforward. So just use F delta x cosine theta. That's the formula for work. Force is 1.20 times 10 to 2 Newton. Displacement is 5 meters. And angle, so angle between delta x and F is 0 degrees. They are parallel. So do the calculation. That gives you 600 joules. Okay, 600 joules. Now, if you pull it at angle, then you will have cosine 60 degrees instead of cosine 30 degrees instead of 0 degrees. Cosine 30 degrees. So do the calculation. That will give you 5.20 times 10 to 2 joules. Okay. So you see here that you do more work when you pull it horizontally. Okay. And when you pull it at angle, you do less work. And sometimes you may also have negative work. For example, let's say there's an object moving this way, and let's say the friction force is being exerted in the opposite direction. So delta x is to the right and friction force is to the left. So in this case, work is F delta x cosine. So the angle between F and delta x is 180 degrees. They are opposite to each other. So the value of 180 degrees is -1. So in this case, you have negative value. That means work is negative. So when displacement and force are in opposite directions, work done is negative. So we'll see example of that in a second. So now let's look at number 5. So not 5, sorry, number 3 first. Number 3. So let's draw free body diagram for number 3 first. So there's a box. So denote that box by this point. So let's consider that this is positive x-axis, and up is positive y. So there is weight of the box vertically down. There is normal force pointing vertically up, and the arrows should be equal because the box is not moving up or down, or there is no acceleration up or down. So these arrows need to be same. It's in equilibrium in the y direction. Although my arrows do not look same, but they need to be same length. And there is friction. In this case, it's kinetic friction. It's sliding, so we have F sub k. And there is tension, and the tension is at 30 degrees. Okay, so that's the free body diagram. So what we need to find here? We need to find the work. Okay, so W is what? So work done by this tension is W is equal to T. It's asking how much work is done by the person. That means the work done by the tension, because the person is applying force through the tension of this string or through the rope. So T displacement is delta x cosine 30 degrees. Okay, so that's what we want to find. But the question doesn't give us tension. So first we need to find tension. So find T first. So to find tension, let's use the idea that we used before. Consider this as a force problem. So write the Newton's second law for x and y direction. So F sub x is max, that's in x direction, and F sub y is equal to may, that's in the y direction. So what are the forces we have along x direction? We have this friction force F sub k, and it's negative because it's pointing to the left. And then we also have x component of this tension. X component of the tension is T cosine 30 degrees. That's the x forces. That is equal to max. Do we have any acceleration? If you read the question, it says the box moves at constant velocity, okay, or the crate moves at constant velocity. So acceleration is 0 because it's constant velocity. So T cosine 30 degrees is equal to F sub k. Okay, I'm taking this to the right, and this thing is 0. So let's call this equation 1. Now let's write this equation for y component. So we have normal force pointing up, weight pointing down, and there is y component of this tension, which is plus T sine 30 degrees. Okay. So weight down, normal force up, and this T sine theta also up. So this is tension. It has this x component, this, and this has y component. Okay, so x component goes here and y component here. Okay, that is equal to 0. There is no acceleration in upward direction. So So then we can write N. Let's look at this one first. So we want to find tension. So to find tension we need friction, but the friction is not given, but we know the formula for friction. Do you guys remember the formula for friction? Friction is, yeah, coefficient of friction times normal force. Okay, that's the formula for friction. So mu k times N. So to find T we need N. So we can use this equation to get the expression for N, and then use that in this expression. So write this in terms of N. So N is equal to, these things will go to the right, so minus becomes plus and this plus becomes minus. Okay, let's call that equation 2. So use this, use N from equation 2 to equation 1. So let's do that. So we have T cosine theta is equal to mu k. N is that. Okay, so W minus T sine 30 degrees. So now all we need to do is put T on one side and everything else on other side, because we want to find T. So put T on one side. So why don't you guys do that? So tell me, solve this and get an expression for T, and tell me what expression you get. So how would you do that? So you can write this as, this is cos 30 degrees. So you can distribute this mu to both these terms, because we want to get this T with this T. So mu k weight, you can write weight is equal to mg, okay, minus mu k T sine 30 degrees. Okay, so put this term and this term on one side. So T cosine 30 degrees, bring this to the left. Now you guys should be able to give me the expression for T. So tell me what will be the expression for T. Yeah, so mu k, yeah, T, sorry, cosine 30 degrees plus mu k sine 30 degrees, right? So that's what you get. You'll get T and T outside the parentheses, and then you will be left with cosine 30 degrees plus mu k sine 30 degrees, which you will bring to the bottom here. Okay, so if you want to do one more step here, it would look like T cosine 30 degrees plus mu k sine 30 degrees is equal to mu k mg, and then you get that expression. Now plug in the numbers, all the values are given. Mu k is 0.55, mass 40 kilogram, g is 9.8 meters per second squared, cosine 30 degrees plus mu k is 0.55 times sine 30 degrees, and that will give you tension. So if you do the calculation, you get 189 Newton. Okay, I may be wrong, so please double check that. Okay, so So once you have tension, now you can find work. So work is the tension, because the person applies the force through the tension. So tension, displacement, cosine 30 degrees. That's the work. Okay, work is defined as F delta x cosine theta. That's what we are using here. So tension is 189 Newton. Displacement 7 meters. Cosine 30 degrees. So let's find that out. So what do you get? 189 times 7 times cosine 30. Is that 1150? Okay. Rounding, if you round off, you will get about that. Okay, so let's look at number 5. So please read the question. The driver of a 1,000-kilogram car traveling on the interstate at 35 meters per second slams on his brakes to avoid hitting a second vehicle in front of him, which had come to rest because of congestion ahead. After the brakes are applied, a constant friction force of 8,000 Newton acts on the car. Ignore air resistance. At what minimum distance should the brakes be applied to avoid a collision with the other vehicle? If the distance between the vehicle is initially only 30 meters, at what speed would the collision occur? So this problem could be solved in a couple of ways. You can use kinematics to solve this problem, but here we'll be using an easier way. Okay, easier way is to use work energy theorem. So for part A, let's use work energy theorem. So work is change in kinetic energy. So work is final kinetic energy minus initial kinetic energy. Now, what force does the work in this case? What causes the speed to change? In this case, the speed decreases. Brakes, or the force applied by brakes is friction, right? So friction causes the change in kinetic energy. So that means the work is done by friction. So we know work is F delta x cosine theta. So for friction is Fk. In this case, it's kinetic friction because the car is already moving. Displacement is what we want to find. So delta x, and then angle between friction and delta x. So the car is moving this way. The brakes are, or the friction force is exerted to the opposite direction. Okay, so that means theta is 180 degrees. Kinetic friction final 1/2 mv final squared. Kinetic friction initial mvi initial squared. So Fk delta x cosine 180 degrees is -1. The car comes to rest eventually. That means the final velocity would be 0. So 1/2 m final velocity is 0, 1/2 m v initial squared. So here we have minus fk delta x, this thing is 0, and then minus 1/2 mvi squared. So find delta x. So delta x will be, we can cancel minus and minus. So 1/2 mv initial squared over fk. Okay, dividing both sides by fk, we get this expression. So now plug in the values. 1/2 mass of the car, 1.00 times 10 to 3 kilogram. Initial velocity is 35 meters per second. Square that. And then friction force is 8 times 10 to 3 Newton. So that gives us delta x, which is 76.6. Okay, sorry, not Newton, it's meters. So this is the minimum distance the brake should be applied to avoid the collision. Now the second one, let's say we decrease the distance. Okay, we want to decrease the distance. We want to stop even before that distance. Then no, sorry, I think I repeat the question again. If the distance between the vehicles is initially 30 meters, at what speed would the collision occur? So in this case, delta x would be 30 meters. So number 5, part B. Delta x is 30 meters. And we want to find the final speed, okay, final speed at which the collision occurs. So exactly same kind of problem. So work is change in kinetic energy, same thing. Work here again is due to the friction, so minus fk delta x, that's the work done by friction. Okay, that's what we got here, negative f delta x. And then on the right side we have 1/2 mv final squared, 1/2 mv initial squared. So we want to find Vf, so we need to write this expression in terms of Vf. So how do we write this in terms of Vf? So we can bring this term to this side, so minus fk delta x, so this term becomes 1/2 mvi squared is equal to 1/2 mv final squared, and then we need to write this in terms of Vf. So or if you like, you can plug in the numbers and then find Vf from here. Or I can just first write the expression for Vf and then plug in the values to find Vf. So how do I get Vf on this side? So divide both sides by 1/2 m. So cancel 1/2 m and 1/2 m. So that gives me fk delta x, this 2 goes on the top over m, plus this 1/2 m and 1/2 m cancel, so vi squared is equal to v final squared. So let's find Vf squared first and then we'll take the square root of that to find Vf. So let's plug in the numbers in this expression. So negative 2 friction force is 8 times 10 to 3. So that's friction, and then delta x is now only 30 meters. Mass is 1000, 1 times 10 to 3 kilogram. Okay, so that's the first term, and the second term is initial velocity squared. Initial velocity is 35 square. So that gives us 745. The unit would be meters square second squared because it's velocity squared. And then for velocity, you can take the square root of that, 745. So that gives us 27.3 meters per second. So the collision will occur at that speed if the distance is 30 meters. Okay, so that's worksheet 12. So the test will cover up to this, okay? And anything after this would not be covered. So let's talk a little bit about energy now. So we just saw kinetic energy. There is another type of energy which is called potential energy. Do you guys know what potential energy is? You might have heard about potential energy. Any idea what potential energy is? Or never heard about the term? Yeah, potential is a stored energy. And this stored energy comes due to the position or configuration of an object. Okay, it's due to the position or configuration of an object. So for example, let's say you have this surface and you have an object on the surface. You lift the object to some height, to height h. Now, because of this configuration, this object will have an energy, okay, and that energy is called potential energy, PE. Okay, so this potential energy is due to this configuration, due to the height. And how do you know it has potential energy? You know it has potential energy because if you drop it on some object, it will show the effect. Okay, it will do work on that object. So the definition of energy is capacity to do work. So you know an object has energy if it can do work. Okay, if it has capacity to do work. So this object dropped to some other object can do work on that object. Okay, that means it can do work. So it has energy. Likewise, let's say you have a spring. Initially, the spring is like that. If you stress the spring, now the spring will have some energy because of the change in configuration. Okay, and that energy is also called potential energy. And how do you know it has energy? So if you hit something with that spring, it will do the work on that object. Okay, so this kind of potential energy is called spring potential energy, and this kind of potential energy is called gravitational potential energy. So we'll talk about these two types of potential energies in the next class. Okay, next class means on Friday. So that's all for this class, and please do the revision of the worksheets and quizzes for your test. If you guys have any question, you guys can come to my office either today or tomorrow I won't be here, or Wednesday before the test.